Hi class, so this video is going to be over section 5.7. So we're going to look at inverse trig functions. But before we do that, I do want to review inverse functions with you a little bit, just to make us more comfortable for looking at this section. So what I have to help us kind of review is looking at an example. So let's say we're given f of x equals x squared plus 4 for x greater than or equals 0, and we want to write an equation for the inverse, right? So I want to make some notes here. So just refresh from like college algebra is that a function must be a one-to-one in order to have an inverse function. Right? So then just recall about one-to-one, right? So a function is one-to-one if for a and b in the domain of f if f of a equals f of b, then a equals b. Right? So in other words, if we have 2 points that have the same y value, their x value must be the same as well, right? In order for it to be one-to-one, right? This matching. And remember, if we have a graph of a relation, we can tell this by the horizontal line test. Right? So, if I do just like a quick sketch of f of x equals x squared plus 4, right, we would get a graph that looks something like this. Let's say this is 2, 4, 6, 8. Right, we get this parabola that opens up with a vertex at the point 0, 4. Right, so this obviously would pass it would fail the horizontal line test, right? If I draw a horizontal line, there's 2 points here that match up, so it fails fails the horizontal line test. Right? So in other words, f of x is not one-to-one. Right? We can also show this with a counterexample, right? Looking at these specific points and so forth, right? So then what we can do, though, is let's say we want to restrict the domain. So let's just take this half that I'm highlighting in yellow. Let's just take this part of the graph, right? Which is what we were doing, right? We're saying that x has to be greater than or equal to 0. So I'm, restricting the domain of the function, not letting it be all real numbers. Then the graph that we would have would be just this right part, right? The right part of the parabola, right? So it's like half a u, right? Half a parabola. So this would be, f of x equals x squared plus 4 for x greater than or equal to 0. And this now is one-to-one, right? We've made the function be one-to-one by, cutting out that that left part, right? So now this is one-to-one, right? And the reason why I'm going through this example is notice we start out with a function that's not one-to-one, and we restrict the domain to get it to be one-to-one, because this is what we're going to have to do with our trig functions, right? So let me come off to this side now, and so if you remember right, what we were trying to do was work with f of x equals x squared plus 4. And remember, x is greater than or equal to 0, and we want to find the inverse function of f, right? So remember, f to the, it's kind of like negative first power, right? That's signifying that it's f inverse, right? But that's not actually a power, right? Typically, the negative first power, would mean that, like f to the negative first would mean 1 over, f, but that's not the case, right? So this is just notation to mean the inverse function, right? So let me just write something really quick. So so the domain of f, we're restricting to be 0 to infinity, right? So I'll write that in interval notation. And the range of f we can gather from looking at the graph, right? So the range would be the y value. So notice the smallest y values here at 4, and it goes up forever, right? So the range of f would be 4 to infinity, right? And then something you should know about functions, inverse functions, is that the domain and ranges, they switch, right? So the domain of the inverse function is going to be matched with the range of the the function, right? So this would be 4 to infinity, and then the range of the inverse function, right, is going to come from the domain of f, which would be 0 to infinity, right? So those domain and range switch. Right. So now I think we're finally ready to find the inverse function, right? So so we have f of x equals x squared plus 4, right? So remember, the very first thing we do is just replace f of x with y, and then so this we're showing this, right? And then next we're going to switch x and y. And then now we're going to solve for y, right? So I would subtract 4 from both sides. And we get y squared equals x minus 4. And then take the square root of both sides. So this would be plus minus. So we get y equals plus minus square root of x minus 4, right? But remember here, for the range, for inverse function, we're saying that it has to be positive, 0 to infinity. So really what we would have is that y equals just square root of x minus 4, right? And then put this back into the inverse notation. I would have inverse of f of x equals the square root of x minus 4, right? So there's the inverse function, right? So then a couple other things I want to go over that, again, just a review and refresh, that'll help us for this section. So another note is that we can, say let f be a one-to-one function. Then g is the inverse of f if the following conditions are both true. Right? So the first condition is that f of g of x must be equal to x for all x within the domain of g, right? So that's just kind of a short way to write that. So if you don't like using these symbols, right, these symbols here, instead we could just write for all x in the domain of g, right? That's how that's read, right? So like this upside down A looking thing means for all, right? This is a Greek letter epsilon, which means within. So So depending on your familiarity with those symbols, that's what that means. If you keep taking advanced mathematics, you'll learn all sorts of little symbols like that. So then the second condition is the kind of like the opposite, right? So if we do g of f of x, that has to also equal x, right? For all x within the domain of f. Right, so you could just replace this with f if you want to write it out in words. Right, so we can look at kind of like an example of this, right? So f of x was equal to x squared plus 4, and f inverse of x, which we're saying maybe call that g of x, that was equal to the square root of x minus 4, right? So we can kind of demonstrate this, right, with property 1. If we want to look at f of g of x, this would be equal to f of g of x, right? And then, so we're putting g inside of x, so this would be, the square root of x minus 4 quantity squared plus 4, which equals x minus 4 plus 4, which just equals x, right? So that condition holds. And then the second condition is g of f of x. Oops, hang on. The f didn't look too good. Right, which this is equal to g of f of x, which would be equal to, so we're putting the f function inside of g, so we'd have the square root of x squared plus 4 minus 4, right? Which this would simplify down just to be the square root of x squared, which would equal just x, right? So that holds there as well, right? So in other words, we just verified that our inverse function is in fact the inverse function of f, right? That we had gotten, right? So then another thing to look at and kind of check, and I'll go back to the bottom of page 1. Right, so another note here is that the graphs of f and the inverse of f are symmetric about the line y equals x, right? And so I just have a screenshot here from Desmos, an online graphing calculator. So you can see I have, this red is like our f of x with the restricted domain, and then here, so here's f of x, here's f inverse of x, and here's the line y equals x, right? So you can see that they are symmetrical about that line. Right, so those are some properties of inverse functions. So now what I would like to do is think about sine and think about what the inverse sine function would look like. So if we go to sketch the sine function really quick, and if you need to, you can think about having the, like the unit circle, right? So sine are the y coordinates, right? So like here, this would be the point, 1, 0, and then we have the point 0, 1, and then this would be the point, negative 1, 0, and then this would be the point 0, negative 1. Right, so remember, sine has to deal with the y coordinate, right? So we're focusing in on these y coordinates for sine, and then I can just label this. This is 0, pi over 2, pi, and 3 pi over 2, and then this is back at 2 pi and so forth, right? So if we start to think about what the graph of sine looks like, Oops. Right, so we can just, label these. So, at 0, my sine is at 0. At pi over 2, we're at 1. At pi, we're at 0. Right, so I'm just looking at this unit circle. At 3 pi over 2, the y value is -1, right? So we'd be there. And at 2 pi, we're back at 0, right? And then if I want to look at like negative pi over 2, right, I would just be going this way. So negative pi over 2 would be -1. Negative pi would be 0. Negative 3 pi over 2 would be 1. And then negative 2 pi would be back at 0, right? So we can start to fill in, what this sine function looks like. So we get this kind of curve, right? And it's real apparent, right? If I draw a horizontal line through here, it's going to fail the vertical line test, right? So it fails. I think I said vertical line, so I meant to say horizontal line. Sorry about that. So it fails the horizontal line test, right? Where this is, f of x equals sine of x, right? So in other words, f of x equals sine of x is not 1-to-1. Right, so now we're kind of trying to think about, how can I cut this graph in a way to where it is 1-to-1, right? So it turns out that the preferred kind of way is cutting it at negative pi over 2 and pi over 2, because you'll notice if I cut it at these spots, these parts that's in between these green lines would be 1-to-1, right? If I put in, horizontal lines anywhere here, it's not going to cross, right, more than once. Right, so what we're going to say is let's limit the domain to be in between negative pi over 2 and pi over 2. Right, so what we end up getting is this graph. Right, so we have a point at 0, 0. Pi over 2 is at 1. Negative pi over 2 is at -1. We get this kind of graph like this. Right, so this is 1-to-1. Right, and notice that y is in between -1 and 1. Right, it's limited in between there. Right, and then so you might be wondering, what's kind of the inverse to have this inverse function, right? So let's look at maybe potential motivation, right? So let's say we have this scenario where, I don't know, we want to build a ramp where this is 4 feet and this is 3 feet, right? And then maybe we want to try to find theta, right? Try to find the angle that my ramp has to be at in order to make that happen, right? So we want to find theta, given that, so this would be, tangent of theta would equal 3/4, right? Or, this would be Pythagorean triple, this would be 5 feet, right? And you could use Pythagorean theorem to find the hypotenuse. So, we could also say, given that we were just talking about sine, sine of theta would be opposite over hypotenuse, so 3/5, right? Find theta. So we could do that as well, right? So if we're given, if we're missing an angle, that's why we would want to have this inverse function, right, to find an angle. Right? All right, so let me write down a few more things. So let's say we have, y equals sine of x, right? The domain here is, we're limiting it to be negative pi over 2 to pi over 2, right? So that way we have a 1-to-1 function. The range is going to be in between -1 to 1. right? So then when we look at the inverse function, like y equals inverse sine of x, or this is often written as y equals arcsine of x, right? So it's a preference. These two things mean the same thing, right? Maybe, some people might think that -1 power looking thing looks like a power, but really it's not. So we can write arcsine instead, right? So you want to be comfortable with both formats, both notations. So the domain is going to come from the range, right? So the domain of this is going to be limited in between -1 and 1. And the range of the inverse function is going to come from the domain of the function, which would be -π/2, comma π/2. Right? And we saw this, saw this in the guiding example, right? To think about inverse functions, a refresher about that. So now, what I would like to do is I'm going to graph y equals sine of x and arcsine of x and y equals x on Desmos, so you can see the symmetry about the line y equals x. Right, so let me open up Desmos here. Right, so let's graph y equals sine of x. And remember, though, we want to be limited between -π/2 and π/2. Right, so we can type that in. And then we wanted y equals arcsine of x and y equals x. Right, so if I zoom in here, you can see the symmetry about the line y equals x, the green line, right? So the red and blue line are symmetrical about the green line. All right. So then let me come off to the side here. I'm going to write something up a little more formal about the inverse sine function. So I believe this is just taken directly from the textbook, right? So, so the inverse sine function, right, is what we're focusing on here. So we could say the inverse, oops, it's not showing up very good. The inverse sine function or arcsine, denoted by inverse sine or arcsine is the inverse of the restricted function y equals sine of x for x in between -π/2 and π/2. Right, and remember, without that restriction, we wouldn't have an inverse function, right? Because in order for a function to have an inverse function, we need to be 1-to-1, right? So then we could say, therefore, y equals inverse sine of x is equivalent to, logically equivalent to, sine of y equals x, right? And then, or we could, say that y is equal to arcsine of x is logically equivalent to sine of y equals x. Right? We could say this, where x is in between -1 and 1, and y is in between negative pi over 2, pi over 2. Right? So when you see this symbol, it's like an arrow back and forth. This means a logically equivalent. Statement. And you might see this in textbooks, like if and only if type of statements. And a lot of times in mathematics, we abbreviate it with an if with two F's, right? That means if and only if. Right, so basically what that means is it goes in both directions, right? So we can, take this statement going, whoops, that green isn't showing up. There you go, going this way, but we can also go this way with it, right? It goes both ways. So like an if-then statement normally just goes one direction, right? Where if and only if goes both ways. Right, so that's going to be a useful and helpful statement, right? Knowing that fact that we can go back and forth. So now I'm ready to work through some examples. So we have example 1. So find the exact values or state the expression is undefined. Right. So part A, we have inverse sine of radical 2 over 2. Right. So something that can make this useful is you can I could say let a variable, let's say y, equal inverse sine of radical 2 over 2, right? So in other words, I'm trying to find the angle that gives me a sine value back of radical 2 over 2, right? So then, that would give me that sine of y would equal radical 2 over 2, right? Following the this expression over here. Right, so we're looking at this line here, just rewriting it. And of course, my x value is between -1 and 1, right? Radical 2 over 2 is in between those. So we're good there. So this would be for, y value that's in between negative pi over 2, pi over 2. So we're going to think about, where do I get that sine value of radical 2 over 2? So radical 2 over 2, right? When I think of radical 2, I'm thinking of the 45, 90-degree triangle, right? In other words, pi over 4, pi over 4, pi over 2 triangle, right? So this is 2, across from pi over 4, these are both radical 2's, right? And if I wanted to, multiply everything by a half, I could get a similar triangle where this is radical 2 over 2, radical 2 over 2, and 1, right? So thinking about an angle between negative pi over 2 and pi over 2, right? So in other words, if I draw my unit circle, I'm stuck in between negative pi over 2 and pi over 2, right? So I'm just in between these, first and fourth quadrant. Since sine of y is positive, so this part is positive, I know I'm going to be in the first quadrant somewhere, right? And I want to find, a data point where the y coordinate is radical 2 over 2, right? And it turns out, in the unit circle, the x value is also going to be radical 2 over 2. And this unknown angle y is pi over 4, right? So y equals pi over 4. Right, just thinking through some things that we already know from the unit circle, right? So in other words, inverse sine of radical 2 over 2 is going to be equal to pi over 4, right? Which is what we were after. All right, so the next one, we have arcsine of -1. So just remember, this is the same thing as inverse sine of -1, right? So we could do a similar thing, right? We could say, let y equal arcsine of -1. So since negative 1's in between negative 1 and 1, we could say, then sine of y is equal to negative 1 for y values that are in between and pi over 2. Right? So in other words, if thinking about my unit circle, I'm still stuck in between here, the first and fourth quadrant. And we want a y value of negative 1, right? Y coordinate, because we're dealing with sine, so that would be down here, right? So in other words, this point is 0, negative 1. So with sine, we're dealing with the y coordinate in the unit circle, right? So basically what I'm saying is what we know is that sine of negative pi over 2 is equal to negative 1, right? So and that's what we were trying to find, right? So in other words, so y equals negative pi over 2. So this means that arcsine of negative 1 is equal to negative pi over 2. Right, so we're trying to find the angle that gives us that value back for sine. Right? So then the next one here is inverse sine of negative 3. So, if you recall back from some things that I had written about arcsine, right, we said that arcsine, for y equals inverse sine of x, we said that x has to be in between negative 1 and 1, and y is in between negative pi over 2 and pi over 2, right? So if you notice, the x value is what's inside here, right? In this case, it would be negative 3, right? But negative 3 is not in between negative 1 to 1, right? So in other words, what we could say is, let y equal inverse sine of negative 3. We need to find an angle, that's in between, we need to find an angle y such that sine of y equals negative 3 for y in between negative pi over 2 and pi over 2, right? However, sine of y has to be in between negative 1 and 1 for any angle y. Right, we know this is true, right? We look at the graph of, sine, right? If I come back up here to the graph of sine, remember this oscillates between negative 1 and 1, right? It never goes above 1 or below negative 1, right? So what this means is that inverse sine of negative 3 is right. So we get undefined for that. Oops. Make sure I'm still recording. Yep, we're good. All right, so what we have next for objective 2 is we want to think about something similar for cosine and tangent. So as you can imagine, looking at those graphs, we're going to need to restrict tangent and cosine as well, right? Because they're not one-to-one functions either, right? They would both fail the horizontal line test, right? So, we could say similarly, we need to restrict the domains for cosine and tangent to have one-to-one functions. Right? So if we were to look really quick, just a reminder of, let me get rid of these functions. So if we just type in, y equals cosine of x. Oops. There. Put that here. Oops, it didn't go in. All right, let me grab my keyboard. Right, if we just zoom out, right, you'll notice that if we go in between, negative pi over 2, so I can change this where the x will go, let's say between negative 2 pi and 2 pi. And the x step we want to be pi over 2. And then for the y, we'll just let that be negative 1 to 1. And the step being 1. Right, so we get this graph here. So you'll notice, see if I can, I don't think I can write on this screen here. What I can do, just copy the screen. Let me throw this into OneNote. Right? So by talking about this graph, before we limited between negative pi over 2 and pi over 2, but you'll notice if we keep that same limited domain, this is going to fail the vertical line test or the horizontal line test, right? Which means it's not one-to-one. So, with cosine, what we typically do is go between 0 to pi, right? So if I limit it between 0 and pi, you'll notice that, this area, this part of the graph will be one-to-one, right? So that's the most logical thing to do. Right? So let me just go back here to our notes. Oops, didn't jump over. There we go. Right. So with that, we want to restrict the function y equals cosine of x to be in between 0 and pi. Right? So that means that y will be in between negative 1 and 1. Right? So the graph of y equals cosine in between 0 and pi will look like this. right? Will look like that. And then, similarly what this will mean is that if I have y equals, inverse cosine of x, the x value, the domain, will be in between -1 and 1, and y value will be in between 0 and pi. Right? And you could graph this on Desmos with the function y equals x and see that they're symmetrical, right, about that line. So then with tangent, right, what we're going to end up doing is we're going to restrict y equals tangent of x to be where x is in between, -pi/2 and pi/2. Right, that's what works out the best, right? Because if you remember right from the graph, where here's pi/2, here's -pi/2. These are vertical asymptotes here, and then tangent looks something like this, right? So that's going to be a one-to-one function, right, in between. But notice I didn't include -pi/2 and pi/2 because those are where vertical asymptotes are at, right? So then y, though, in this case, it's increasing and decreasing without bound, right? So y is in between -infinity and infinity, right? So then, so remember here that, this is a vertical, we have vertical asymptotes at x equals -pi/2 and pi/2. Oops. Right, so then when we go to talk about inverse tan, oops, I'll do it over here in the black, it'll show up better, of x, my x value is going to be in between -infinity and infinity, right? Because the x and y switch, right? And then, so that means my y is going to be in between whatever the x was in between. So that was -pi/2 and pi/2. And these vertical asymptotes now become horizontal asymptotes. So we're going to have horizontal asymptotes at y equals -pi/2 and y equals pi/2. Right? So those are the differences between those, right? And like I said before, right, just note that, tangent, inverse tan of x, that's not an exponent. This is not equal to, 1 over tangent of x, right? Inverse negative, like the -1 power, like the tangent, right? This equals the inverse of the tangent function. All right, so I just want to keep that in mind. All right, so what I have next on the next page is just a nice table that shows everything that we've talked about thus far. So for time's sake, I'm just going to ask you to refer to the completed notes on Carmen. So I have, the notes filled in on Carmen, and you could just copy that down into your notes and put everything in this nice table, rather than me spend, 5-10 minutes just copying all that down, right? So what I would like to focus on now is going to example 2. Right. So see Carmen for this table, right? So then example 2, working through some similar examples like we did before, but now we're using cosine and tangent, to help us here. So cosine, so for part A, we have inverse cosine of -1. So we could say, let y equal cosine of -1 of -1, right? This would mean then that cosine of y would be equal to -1 for y in between 0 and pi, right? We can do this because -1's in between -1 to 1, right? So if we think about, a unit circle, we're stuck on between 0 and pi, so just this part in green here, right? We're just focusing in on this part. That's what we're limited by. We want to find an x-coordinate we're at -1, right? Which would be, at this point here, -1 comma 0, and this would be occur at pi, right? So in other words, cosine of pi would be equal to -1, right? In fact, would be lots of angles where cosine of that angle is equal to -1, but since we're limited, between the first and second quadrant for cosine, there's only one possible answer, right? Pi. So in other words, y equals pi, right? So what this means is that inverse cosine of -1 is equal to pi, which is what we were after, right? So then the next one that we have inverse tangent of -√3/3. So I'm going to start these out the same way, right? So I could say, let y equal inverse tangent of -3/3. Then, we would have, tangent of y equal to -√3/3, right? And this would, of course, be, 4y in between -pi/2 and pi/2, and not including those values, right? So if I go to draw like the unit circle, right? Remember, we're stuck in between -pi/2 and pi/2, so the first and fourth quadrant. So similar to sine, and then my tangent value is negative, so I know I'm going to be down here, right? Somewhere in this value. So when is tangent? When does it have to deal with radical? Like square root of 3, right? So I would, draw like my special right triangle. So pi/3 and pi/6, that one has to do with has a square root of 3 in it, right? So across from pi/3 we have radical 3, across from pi/6 we have 1, this is 2. So then, we're trying to think, and remember that tangent of theta is equal to sine theta over cosine theta, right? So if we say, let's say pi/6 is theta, let's see if that works out, right? So tangent of theta would be equal to, so I guess we don't even have to do the, sine over cosine. Tangent is equal to the opposite over the hypotenuse, or excuse me, opposite over adjacent, right? The TOA, opposite over adjacent. So then that would be 1 over radical 3. Right? So if I multiply, rationalize the denominator, multiply by radical 3 over radical 3, we get radical 3 over 3, which is, what we are looking for, right? So really, what we need is pi/6, right? So in other words, this angle here, right, that angle there is pi/6, right? So that's kind of like the reference angle. So we're going minus pi/6 degrees, right? So in other words, the y value is equal to -pi/6, right? So then what that tells me is that this guy equals -pi/6. All right, so then the next one, we have arctangent of 0. So, let's let y equal arctangent of 0. Then what this tells me is that tangent of y is equal to 0. For y in between negative pi over 2 and pi over 2. Right? So, if we think about, tangent of theta as being sine theta over cosine theta, I want to know, when does this equal 0? Well, this is going to equal 0 when sine of theta equals 0, right? So if we think about like the unit circle, sine is the y value, right? So if we're stuck in between negative pi over 2 and pi over 2, at what point in the unit circle is the y coordinate 0, right? Well, that happens at this point here, right? That's the point 1 comma 0. So, and that's at 0 radians, right? So in other words, tangent of 0 is equal to, 0 over 1, which is 0, right? So arctan of 0 is equal to 0. And that's what we are after. All right, so then this next objective is being able to approximate inverse trig functions on a calculator. So let me show you how to do that. So let me grab my keyboard here, and then I'll go split screen with my graphing calculator. All right, so we want to use our graphing calculator to approximate the function values in both radians and degrees, right? So first of all, let's do radians and degrees. Oh, let me get a different color. All right, so we want inverse tan of negative 7.92, and same thing here. So just want to make sure you're in the right mode, right? So if I want radians, let's make sure my mode is in radians. So I would just do second tan, right? Notice that's inverse tan, and then just type in negative 7.92. Right, so we get, roughly negative 1.4452. Right, we'll just go to 4 decimal spots. Right, and then if I want to do the same thing in degrees, I just need to go to mode, switch that over to degrees, and then I'm just going to hit second enter. That'll just do the last entry, and that comes out to be roughly negative 82.80 4 degrees. I'll just do 3 decimal spots there. Right. So then same thing here. We have arc cosine, which remember that's the same thing as inverse cosine of 2/7. Right. So for radians and degrees, right, we can get these. So we would do inverse cosine of 2/7. So my calculator is already in degree mode, so I'm just going to type in second cosine 2 divided by 7. So we get approximately 73 we'll just say 4 degrees, 0.4 degrees. And notice, if you don't know, this equal sign with the dot above, right, that means approximately. So, you could do the wiggly equal sign or equal sign with a dot. So then, inverse cosine of 2/7 for radians. So I just need to change my mode to radians. So we get approximately 1.2810, right? So you'll notice that we can't always get exact values for this, so that's why we want to make sure that you're comfortable doing this in a calculator, right? So last one, radians, degrees. So inverse sine of negative 0.81. All right, we can get this. So right now I'm in radian mode. So second sine of negative 0.81. We get approximately negative 0.9442. And then switch this over to degrees. We get approximately negative 54.096 degrees. All right. So I think, let me see how we're doing on time. 57 minutes. All right. So let's finish up a little more, and then, whoops, probably should have kept that calculator. So let's finish up this example 4, so this objective, and then I think we'll, I'll split the video in 2 here because we got quite a bit left. So example 4, we're told to use a calculator to approximate the degree measure to 1 decimal place or rating measure to 4 decimal places of angle theta, subject to the given conditions. Right. So for part A, we have sine of theta equals negative 3/7, and theta is in between 180 degrees and 270 degrees. Right. So theta is going to be in degrees. Right. So very first thing, let's make sure my calculator is in degree mode. So if I do inverse sine of negative 3/7, that will give me, possibly theta, right? So this will give me, so if I do second sine of negative 3/7, that gets me to negative 25.3769 degrees, right? So that's not in between 180 degrees and 270 degrees, right? Remember, that inverse sine, right, is restricted in between negative pi over 2 and pi over 2, right? Or in other words, negative 90 and 90 degrees, right? So we're restricted in between here. So what we found is that all students take calculus, right? So so sine is negative in this fourth quadrant, right? So this part was 25.3769 degrees. But what I want is I want to get the same y coordinate, right? Or be in between 180 and 270. So that would be here. So that reference angle would be the same, right? So what I'm going to do is call this theta bar, which is like the reference angle, right? So this part would be, theta bar, that 25.37 degrees, right? So in other words, theta is going to be equal to, so we would have 180 degrees, right? Because we went, from here to here is 180 degrees. Then I need to pick up this extra bit, which is the 25.37 7 degrees. Right? So if I take, so I'm just going to multiply this by -1, right? Then I'm going to take 180 plus that answer, and we get roughly 205 point, and we're asked to round to 1 decimal place, so 0.4 degrees. Right, so you just have to keep in mind that when you do the inverse trig function, it's going to be stuck in between that given domain, so we just need to meet the given conditions, right? So this next one, we have tangent of theta equals -8/3, right? So don't forget, all students take calculus. Tangent is stuck in between -π/2 and π/2. And down here is where we're going to get the negative tangent, right? So we need to find this angle we'll call theta bar, right, or reference angle. So if I take inverse tan of -8/3, let's see what we get. So just to be clear, this should be in radians, so I need to switch my mode on my calculator. So we'll do second tangent of -8/3, and we get roughly -1.212. Right, so that's what this. So this reference angle is 1.212. So I'm going to multiply this by -1, and then I'm just going to store this as a. Right, so anytime I use a in my calculator, it'll just do that number. Right. So then, we want to think about, we're stuck in between π/2 and pi, right? So we're in this second quadrant. So this part would be, theta bar, the reference angle. So, to figure this out, theta is going to be equal to pi minus, that theta bar, right? Or in other words, theta is equal to pi minus a in my calculator, right? Because that's how I stored it. So if I take pi minus alpha a, we get roughly 1.9. We're going to 4 decimal places, so 9296, and that's in radians, right? So that's what theta would be. All right, so I think this is a good place to stop this video. We're about an hour, so I'll make a part B and finish up these notes. Make sure you let me know if you have questions.